describe the process of conducting a univariate analysis on a given data set. Include the steps involved and the key metrics you would evaluate. Conducting a univariate analysis involves examining a single variable within a data set to summarize and find patterns in the data. Here is a step-by-step guide on how to perform a univariate analysis. 1. Data collection. Begin by collecting the data you intend to analyze. This data could be from a database, a CSV file, surveys, or any other source. 2. Data cleaning. Prepare the data for analysis by cleaning it. This includes handling missing values, removing duplicates, and correcting errors. This step ensures the quality and accuracy of your analysis. 3. Exploratory data analysis (EDA). Start with exploratory data analysis by focusing on the single variable of interest. This can be done using both graphical and non-graphical methods. 4. Graphical analysis. Histograms, bar charts, box plots, pie charts. 5. Descriptive statistics. Calculate key metrics to get a deeper understanding of the data. For numerical data, mean, median, mode, standard deviation, variance, range, quantiles, skewness and kurtosis. For categorical data, frequency counts, mode. 6. Data interpretation. Interpret the results of your graphical and statistical analysis. Understand what the measures of central tendency and variability tell you about the data. 7. Reporting. Compile your findings into a report. Include visual aids like charts and tables along with descriptive text to explain the insights from your analysis. This report should be comprehensible to someone who may not be familiar with technical statistical terms. 8. Decision making. Use the insights gained from the univariate analysis to make decisions or to inform further research. This might involve identifying areas for operational improvements, focusing on certain segments, or planning further detailed analysis. This structured approach to univariate analysis helps in understanding the basic properties of a single variable, which can be crucial for further multivariate analysis or for deriving actionable insights from the data. Explain the use of scatter plots in bivariate analysis. Provide an example of how a scatter plot can be used to identify relationships between two variables. Scatter plots are a fundamental tool in bivariate analysis used to visualize the relationship between two quantitative variables. They help in identifying patterns, trends, correlations, and potential anomalies between the variables. Here is an explanation of how scatter plots are used in bivariate analysis, along with a practical example. Use of a scatter plots in bivariate analysis. Visualizing relationships. Scatter plots display individual data points on a two-dimensional plane with each axis representing one of the variables. This setup allows you to visually assess the relationship between the two variables. Identifying correlations. By observing the pattern formed by the data points, scatter plots can help determine if there is a correlation between the variables. If the points trend upwards from left to right, it suggests a positive correlation. If they trend downwards, it suggests a negative correlation. Assessing linearity. Scatter plots are particularly useful for checking the linearity of the relationship between two variables. A linear relationship will appear as a roughly straight line of points. Detecting outliers. Any data points that do not fit the general pattern of the scatter plot can be identified as outliers. These are important for statistical analysis as they may indicate data issues or special cases. 5. Understanding the distribution. The spread of the data points can give insights into the distribution and variance of the data, indicating how tightly the variables are related. Example of using a scatter plot. Scenario. Let's say you want to analyze the relationship between the number of hours studied and the scores achieved by students on a test. Steps. Collect data. Create a scatter plot. Analyze the plot. Linearity and outliers. Interpretation. From this scatter plot, educators can deduce if additional study time generally leads to better test results, which can inform teaching strategies, study recommendations, and student guidance. Moreover, outliers can be further investigated to understand unique cases or anomalies. Scatter plots thus provide a clear, intuitive way to visualize, analyze, and interpret the relationships between two variables, making them indispensable in statistical analysis and decision-making processes. Explain the concept of dispersion in univariate analysis. Discuss the different measures of dispersion and their significance. The concept of dispersion in univariate analysis refers to the spread of values around a central point within a data set. It provides insights into the variability or consistency of the data, which is crucial for understanding the reliability and predictability of the data. Dispersion helps in assessing the risk, quality control, and decision-making processes in various fields. Measures of dispersion. Several key measures are used to describe dispersion in a data set. Range. Definition. Significance. Interquartile range IQR. Definition. Significance. Variance. Definition. Significance. Standard deviation. Definition. Significance. Mean absolute deviation. Definition. Significance. Significance of dispersion measures. Understanding dispersion is crucial for several reasons. Risk assessment. High dispersion indicates higher risk and unpredictability in the data set. For instance, in finance, a higher standard deviation in stock prices suggests more volatility and risk. Quality control. In manufacturing, low variability is often associated with high quality as products are consistently close to some target value. Comparative analysis. Dispersion measures allow comparison between different data sets or groups within a data set to understand which group is more varied. Data modeling. Effective modeling requires understanding the underlying variability in the data. Dispersion metrics can influence choices about the types of statistical models or tests that are appropriate for the data. Dispersion provides a more nuanced understanding of the data beyond central tendency, offering essential insights into the spread and reliability of the data, which are fundamental for interpreting results and making informed decisions. Discuss the various stages of EDA and the tools and techniques commonly used in each stage. Exploratory data analysis (EDA) is a critical step in the data analysis process, aimed at understanding the main characteristics of the data, discovering patterns and anomalies, and formulating hypotheses. It typically involves a series of stages, each using specific tools and techniques. Here is an overview of these stages and the common tools and techniques employed. 1. Data collection. Tools and techniques. Data sources. Data importing tools. 2. Data cleaning. Tools and techniques. Handling missing values. Dealing with outliers. Data type conversions. Data transformation. 3. Data profiling. Tools and techniques. Summary statistics. Data profiling tools. Data visualization. 4. Data visualization. Tools and techniques. Univariate visualization, bivariate visualization, multivariate visualization, visualization libraries. 5. Data transformation and feature engineering. Tools and techniques. Variable transformation, feature creation, dimensionality reduction. 6. Correlation and causation analysis. Tools and techniques. Correlation matrices. Causation insights. 7. Hypothesis testing. Tools and techniques. Statistical tests. Confidence intervals. 8. Iterative analysis. Tools and techniques. Iterative modeling. Advanced visualizations. Commonly used software and libraries. Python libraries. R packages. Data visualization tools. Each stage of EDA is crucial for ensuring that the subsequent statistical analysis or machine learning modeling is based on a thorough understanding of the data's underlying properties and relationships. This approach helps to maximize the effectiveness of the predictive models and insights derived from the data.